To thank everybody for joining the webinar today. It's Simulation and ByWire Vehicle Testing for Comprehensive Validation. And our presenter today is Jeff Blackburn. He's the VP of Sales at Dataspeed, which is a leader in autonomous vehicle by-wire technology and integrations. This webinar is part of a series of webinars that's been based on the work of the IEEE Standards Working Group P2784. And Jim Fraser is the chair of that working group, and I'll introduce him in a second. My name is Dan Toland. This webinar is also jointly facilitated by ARC Advisory Group, which Jim is part of as well. A couple administrative areas. All lines are on mute right now to prevent background noise, and I am recording today's webinar. And people will get copies of the slides in PDF format after the presentation as well. So that'll be going out to everybody today. I will now kind of turn it over to Jim. We will have a questions and answers at the end of the session. Please use the Q&A function, which is in the bottom right-hand portion of your screen typically. And we can go from there. And then I'll introduce Jim, who can then kind of introduce Jeff more formally as well.
Well, thanks, Dan. As Dan had mentioned, this continuing series happens every 2 weeks on a Tuesday Eastern at 11 a.m. And it's meant to drive participation and support of the IEEE P2784 Smart City Planning and Technology Guide. It's a bit unique standard in the world of the IEEE because it's meant as a cookbook for public agency officials, from public works directors to city managers, to help them find what do you do first on day one when you want to build a smart city. What drives economic viability and environmental concerns and jobs for that matter, as well as quality of life. So our next face-to-face meeting is February 6th in Orlando, Florida. Feel free to reach out to me for details on that. And without further ado, I'm very impressed and very looking forward to this presentation today by Jeffrey Blackburn, VP of Sales at Dataspeed, on simulation and by-wire vehicle testing for comprehensive validation. So Jeff, take it away.
All right. At least for those of you on the East Coast, good morning. What we're going to cover today is basically 4 points. We want to look at autonomous vehicle simulation testing, why it's used, why at least I and most of the industry believe that there is an absolute need for simulation testing with respect to developing autonomous vehicles. I want to touch a little bit on what some of the limitations are of that testing. I then want to talk about what's known as a by-wire vehicle testing and how that needs to be combined with the simulation testing to ensure that the actual results that you're seeing from simulation, in fact, that there's a good correspondence with actual real-world results. And then I'll talk a bit about how to evaluate the testing results and what I think are some keys to ensuring an accurate testing and validation process. So to start off with on our first objective, let's look at autonomous vehicle simulation testing and really why this is used and why it's needed. So if you look at a typical autonomous vehicle that's currently under development, and I'm talking about what the SAE, at least in their standards, will define as a level 4 vehicle. So this is a vehicle that can drive by itself. It does not rely on any of the human occupants to be available to take over control if something goes wrong. That essentially the vehicle can perceive the world, it can navigate, it can drive by itself, and should something happen that needs to be corrected, the vehicle can deal with that independent of any human interaction. That's an extremely challenging development and verification task. To just give you an idea of the complexity that we're talking about, if you look at If you look at a modern high-end sedan that's currently being produced, that car will have about 100 million lines of code on board, running in over 100 electronic control units. It's probably the second most complicated code base that you'll ever interact with in your entire life. The most complicated is likely if you're a user of any of Google's services. Their code base is upwards of 5 billion lines of code at this point. But a modern car is an extremely complex device, and a modern car that can drive by itself is an order of magnitude more complex than where we are right now. What simulation lets you do is basically easily and cheaply, it provides a way of testing this gigantic amount of code. So for instance, as we're going through our development process, we've got things working well, we make a change to one of the pieces of the AV stack, which I'll show you in a moment. That typically will require us to go back and do some regression testing to ensure that the changes that we made didn't break something else. And that's where simulation tools are so incredibly valuable, because it allows you, particularly if you're using any kind of modern software development processes, the term you'll sometimes hear is DevOps, it allows you to automate much of this regression testing. And in fact, you can automate a lot of the simulation testing required as you're developing code. Just another example to give you the kind of complexity that I'm talking about. Let's think about this notion of what is known as a behavioral competency. So NHTSA, actually a group known as California Path, doing some work for NHTSA, has identified 28 behavioral competencies. And then Waymo and some other folks have come up with an additional 19. So currently, roughly we have 47 of these things. An example of a behavioral competency is the ability to do a high-speed merge. The autonomous vehicle can do a high-speed merge onto a freeway. That's something that any self-driving car has to be able to perform competently. If you think about that test case, so merging onto a freeway, and you assume that there might be, in my example, 8 relevant variables. These variables could be things like traffic density on the expressway, traffic speeds, the color of vehicles, weather, things like that. And for each of those different variables, if you can imagine 5 possible values, simple math will show you that just with those, and I would suggest these are very conservative estimates, that'll give you 400,000 unique test cases to prove out this one competency. Assuming that you then need 10 different scenarios, so think of physical changes in the lane feeding into the expressway. You end up with about 4 million test cases if those 10 scenarios cover all of the possible variations to prove out one behavioral competency. There's 47 of them. This means that you have about 200 million test cases that you need to run to prove that your vehicle can drive in a fashion similar to human beings. This is just an example. No one really knows how many tests are going to be required before we get to well-behaved level 4 vehicles. There are groups that are working on establishing common libraries of testing scenarios. 2 that I'll mention is Pegasus Group, which originated with some of the German OEMs. And then Society of Automotive Engineers, SAE, also has a simulation working group as well. I touched on this a bit, but input conditions for a simulation. These would be things like the physical road network, road markings, buildings, signs, all of those attributes that make up the scene. And I'm going to run a little movie to show you what's currently available in terms of simulating input conditions with one of the virtual testing tools that are out there. So as you can see, you can vary the quality of road markings, whether the roads are wet or dry, traffic, types of vehicles, lighting, the color of vehicles, time of day, etc. I mean, it's it's still this particular example that I'm showing you uses the Unity rendering engine, which is one of the two large gaming engines that are out there. But it's getting better as we continue on. It's getting more and more photorealistic in the ability to actually turn out a simulation that looks like the real world. Second thing that we want to look at in terms of simulation is the mechanism. This is the actual function or AV feature or piece of software that we're testing. And to give you an idea of the complexity of an autonomous vehicle software stack, this is a graphic that shows the Apollo 3.0 AV stack. Apollo is a product that originally came out of Baidu. So this is an open source piece of software, and each of these small blue boxes that you see under the open software platform. So you'll see there's a piece that says localization, perception, planning, control. So, as an example, let's look at the perception box. It looks like a very small piece of the overall stack, but that box by itself is all of the code required to take input from cameras or radar or LiDAR and convert that raw data into meaningful data in a manner analogous to, in the case of a camera, your eyesight. So it's taking image frames from the scene, fed to it by the camera, and it's actually deriving useful information from that scene. It's identifying cars and people and other objects in the scene as part of that perception function. So this is not a trivial piece of code, and it is not a trivial task to try to test this going forward. And the last piece of the simulation is we need to be able to simulate output conditions. By output conditions, I'm referring to control of the vehicle's longitudinal and lateral motion. So throttle, brake, steer, shift. We need to somehow, as we're running the simulation and we've made a control decision, we then need to send an output to our virtual vehicle to command it to turn left or turn right. Give you an example of that. This is a lane keep assist example. So this little movie that you're going to see uses a camera. It is perceiving the scene in front of it, and it's passing image frames at about 20 hertz, 20 times a second, to the perception stack. The perception stack is then identifying where are the lane markings in the image. Once it identifies the lane markings, some additional code compares the location of the lane markings to the position of the current position of the vehicle. And then in order to keep the vehicle centered in the lane, as it sees movement in the left or right direction, commands are sent to steer the vehicle left or right. So let me run this. You can see how this operates. So it's looking at the incoming data, and as we enter the curve, you'll see it will begin to command, in this case, a right steering angle at some degree to keep the car centered in the lane. So even though it looks relatively simple, there's a lot going on in the background. And in order for this to actually work in a real car in the real world, all of those pieces that I mentioned, the input conditions and the output conditions, all of those have to have very good correspondence with how the real physical world operates. So one other thing that I want to touch on with respect to simulation and why it's useful and why we want to use it is if you think about behavioral competencies and the many millions of tests that you need to run, that is a very expensive proposition. Simulation would hopefully allow us to narrow down or sort of narrow down the funnel of the actual physical tests that we need to run. And it will allow us to do lots of testing in a very short period of time compared with running actual physical tests. Let me now show you an example of sort of how this works, and then I want to talk about two approaches to simulation. One is a workstation-based approach, and one is cloud-based. So this is a workstation-based example. In this example, again, the perception stack is attempting to determine is there something in front of us? Do we need to apply the brakes? You'll see in the upper left, you'll see a graphic representing a simulated radar, and then on the right-hand top is the image frames coming in. And as I run this, the gentleman's running out in front of the oncoming truck. We perceive that he's there. We try to apply the brakes. In this case, it appears we may have hit our virtual individual, but the idea is to slow down and ideally not hit the person. Same situation, there's lighting above where the person emerges into the lane. In this instance, we've eliminated the lighting, so we've changed one of the variables. And you'll notice in a workstation-based approach, these all run serially. So we run test 1, then test 2, then test 3, then test 4, changing different variables from run to run. So here's rain, fog, snow, etc. So this is a use example of how you might, in this particular instance, you're checking your perception stack and your controls in this one given scene, and you want to run all these different variations. And as I said, you can do this if it's a workstation-based simulation tool. You're going to do this serially. If it's a cloud-based tool, each of these different tests that you've seen can all be queued up and can be run simultaneously. So if you've seen anything about Waymo and their car craft tool and how they're doing simulation testing, this is what folks like Waymo are doing. They're running millions of test instances overnight, and they're doing that on a continuing, ongoing basis over and over and over. This gives them tremendous ability to cover many edge cases, many combinations, and they can begin attacking that problem of, for instance, if we use behavioral competencies, of the 400 million tests that we need to run. So that gives you an idea of why simulation is so extremely valuable. But now I want to touch on some limitations when it comes to using simulation. The thing that you have to consider here is that simulation is only useful if you have what I'll term good correspondence with the real world. So essentially what we're saying is the mathematical models that are used to model the sensors must in fact behave in a manner similar to the way the real sensors work in the real world. The virtual scene that's been built the material properties, the specular versus matte surfaces, whether something is metal or plastic or paper. All of that information has to be incorporated into the simulation to ensure that we're not running a simulation that is essentially useless because it doesn't reflect the real results we're going to be when we go and run the vehicle in the real world. Let me touch particularly on sensor models. So as I mentioned, I'm a founder of one of the simulation companies. And the difficulty that all of the simulation companies have is that they're relying usually on published research coming out of the universities in terms of guidance in how to build the sensor model. Their expertise typically is in graphics and 3D modeling capabilities. They don't usually have access to physical laboratories or test vehicles. And in many cases, they don't even have the actual sensors themselves. And this can result in models being built that, since they don't have good correspondence with the way the actual sensor works in the real world, can give you false or misleading results when the simulations are run. Sensor models typically are built in 3 forms. So the first would be what I call a non-realistic perfect model. So if this is a radar, essentially what this non-perfect model will tell you is that there is a target in front of the vehicle at some range or some distance from the vehicle. And it will tell you that every single time, regardless of the actual scene that's in front of it, the virtual scene. Not a very realistic model because that's not how radar works in the real world, but there's at least some utility to that kind of simple sensor modeling. The next step up from that would be what you could think of as a probabilistic model. So this is a model that uses some information from data sets of real sensor data. And what it does is it doesn't physically recreate the actual functioning of the radar, of the real radar, but instead it overlays a layer of probabilistically correct noise on top of the actual signal in an attempt to make it closer, the simulation model closer to the way the real sensor works. And then lastly is a full-blown physics-based model. These are very difficult to build, and typically they're very computationally expensive, but they are an actual physical model of how the radar works in the real world. The problem is that computationally intensive model is slow and very, very complicated and expensive to build. So what happens is that generally you're looking at models that are simpler recreations of the sensor that we're trying to create. Give you an example. If we're modeling a radar and we have this situation, the pedestrian that you see in front of the vehicle, typically you don't get much return in the real world from a real radar. You wouldn't know that a person is standing there. But we understand that, and even with simple models, this is relatively easy to model. If we make it a bit more complex, so we have another vehicle in front of that person, then what you're going to get, you'll see the white van, but you won't see, again, the person in between the 2 cars. The question becomes, how do we model this relatively straightforward, simple condition, as well as this more complicated condition in a virtual radar given these two different scenarios? And that's the challenge that the simulation companies are facing. Like I said, the way this is generally approached in the better quality models is to use what's known as a probabilistic sensor model. This is how that works. So in this case, you'll see on the top, you'll see two cars that are converging on each other. And the blue sort of cone, that's the radar beam of the car looking at the car approaching it. As I start this, the top graph charts the actual, the top left black box that you see, that's charting the actual range between those two vehicles. And I apologize that the legends are really too small to see, but it's in meters. The bottom chart that you see with all the different colors, that's the top actual range, and on top of it is superimposed this probabilistic noise model. So the bottom is what we would pass to the perception algorithm, and we would force it to process that data to derive a correct range. And then on the right, you'll see graphically, you just see these little circles that you see. Those represent clutter. So that's the noise that the radar is picking up as the simulation runs. But this is currently for simulation sensor modeling. This is pretty much state of the art. Show you one other example that's a bit more complicated. This is again a radar example, and this is showing you what's known as range Doppler output data. So this is taking simulated raw radar data model, and it's processing it, and what you see on the right-hand side is what a radar engineer would expect to see in terms of process data. So as I run this, you see the scene in front of us, and on the right-hand side, you have to imagine we're looking down on top of our car. And you'll notice the speed, there's a line at 15 meters a second. That's how fast we're moving. As we come up and approach this building, we're going to be turning left. And you see these cars coming past us. That's the bright yellow that just went past us. As we turn, you'll see a very sharp V form. That will be the edge of the building in the return that we're getting off of both sides of the building as we go through the turn. It's right there. And what you're looking at, even though it may appear to be somewhat cryptic and noisy, this is considered to be processed radar data. So this is what a radar engineer would expect to see looking at radar signals, at processed radar signals coming in. So there's one simulation company out there that's capable of doing this. I want to try and stay non-commercial, so I don't really want to say company names, but contact me after the fact, and I can tell you who to go see if you have a need for this in your company. Next, I want to talk about how to combine ByWire enabled vehicles and use them as a mechanism to check and validate your simulation results. So, by a ByWire vehicle, what I'm actually talking about is a vehicle that has been modified so that we can control both longitudinal and lateral control. So we have control of the throttle, brake, steering, and shifting. And we can control this via electrical signals or through sending messages over the CAN bus. So this is a car that has been converted and can be driven by a computer. The reason that you would want to combine ByWire or real vehicle testing with simulation is that presently this is really the only mechanism that's available to do a check on the validity of the simulation results. Um, you might think that you could do this kind of checking using human drivers, and I would suggest to you that human drivers are not repeatable enough in terms of time and position accuracy to be able to be used as the controlling mechanism as compared to a ByWire car. So ByWire Vehicle, if we want to set up a test where we're on a test track and the car is driving some known path, we'll have recorded some GPS waypoints. That car is capable of driving that same drive profile with respect to speed and position, so that the vehicle will be in the same relative position from test to test. So at the same time, it'll be in the same position, roughly within plus or minus 3 centimeters. That's very, very difficult, even for well-trained human test drivers, to be able to operate with that kind of repeatability. But it's this kind of testing that you then compare against an equivalent virtual simulation. So you have the results from the physical test compared against the virtual simulation to establish how good your correspondence is between the real and virtual worlds. Let me give you another data point in terms of how tightly a ByWire capable car can drive compared to human drivers. And this is some data from Tesla. So this is Tesla's lane keep assist. You'll notice the gray distribution are human manually driven vehicles. And it's roughly centered in the middle of the lane. It's a relatively wide dispersion around the mean, and it is skewed actually slightly towards the right lane edge. By the way, this is data from vehicles where it's normal to drive in the right-hand lane, not in the UK in the left-hand lane. The red distribution shows where the vehicle is positioned and how much variability is when autopilot is driving the car under LKA. So as I said earlier, although humans are very good drivers, I think we sometimes underestimate how good humans are in driving. They can't drive with the same kind of repeatability and accuracy that a ByWire vehicle is capable of driving. Lastly, I want to talk about just a couple things in terms of cautions in correlating testing results and making sure that what you're getting from your simulation tests are going to be useful and in fact will reflect what you can expect in the real world. I would caution that you be very careful when you're looking at real world against your virtual results. There are a lot of variables that you have to take in mind that can complicate what appear to be an otherwise straightforward comparison. So, for instance, if you think about buildings in your virtual scene, whether those buildings have material properties attached to them that indicate that it's a specular surface versus a diffuse surface. A specular, I'm talking about shiny. Diffuse would be a brick wall. That's very important depending on the type of sensor you're using. LiDAR in particular comes to mind. Whether the material is wet versus dry can make a difference. You need to look at sensor variability in terms of noise, signal fade with distance, multipathing. Are there multiple sensors in a scene where you might experience crosstalk? Have you taken into effect signal attenuation based on weather effects? An example of this would be using a LiDAR in clear weather versus using a LiDAR in rain, and then versus in fog. when you try to use a LiDAR in fog, the small suspended droplets of water in the atmosphere do an excellent job of attenuating the signal. And then lastly, you also want to ensure that your virtual vehicle itself, that you have good correlation with the real car. Does the simulation incorporate changes in friction coefficient with changes in the weather? In essence, what I'm saying is, if it's snowing or cold, do the roads become more slippery? And it's these kinds of things that I'm just counseling that quite often get overlooked when simulation begins to be used. And only when you've actually compared real world results against an equivalent simulation test, and understanding the limitations and your assumptions, only then should you really begin accepting simulation results as a proxy for the real world. All that being said, simulation is an incredibly important tool used in the developing of AVs going forward. In fact, I would argue that it'll be impossible to develop a level 4 autonomous vehicle without the use of simulation. But that again, you have to be very cognizant and understand all of the assumptions and all of the limitations so that you can make intelligent use of the simulation results. Physical testing is also still going to be required. We're never going to be able to get away from all of the physical testing. It is another validation method to ensure that the AV software is working, and also importantly, it's a check against our simulation results. So, kind of in summary, we've covered why simulation is important and what the limitations are. I've discussed a little bit about ByWire vehicles and how they're useful in terms of development tool and as a check against the use of simulation, and presented a few cautions in terms of evaluating the correlation of the results against real world results. With that, I guess we'll take questions.
Thank you, Jeff. That was very informative. Let's see if some people can type in some questions, either using the chat and or the Q&A function that's part of the WebEx.
Well, I'll take a stab at a question. Jeff, is your simulation and testing efforts, do they apply just to suppliers, or is it application dependent? And I'm thinking through the scenario where we have a number of vendors that are autonomous shuttle providers that limit the interaction to maybe a 3-mile loop or a geofenced area that may not take in all potential conflict scenarios.
Yeah, understand. So, for example, I'll give a shout out, even though I didn't go there, to the University of Michigan. So they're running, they were running, I believe, may still be running, an automated shuttle on their North Campus. It is geofenced. It runs the same loop over and over and over. And it's relatively low speed. It essentially shuttles people from parking areas down to the main engineering complex. What they did is they built a virtual scene that reflected that physical layout. So they modeled the parking lots, the road network that the shuttle will travel on. They had a model of the vehicle itself. They developed models of the sensors that are on that vehicle. And then they ran n number of iterations in simulation before they ever put the vehicle in practice to check that, in fact, how they thought it was going to work, in fact, is how it was working. And this is what they did on an ongoing basis. Once they began running the shuttle, I believe they had a Naviated shuttle, by the way, they would then look at the real-world results and compare it against what they had seen when they ran simulations. And that allowed them to begin fine-tuning the sensor models, and it also helped drive improvements in the actual autonomous vehicle stack that controlled, perception and control of that vehicle going forward. So it's not this can be used. This could be used by simulation could be used by the sensor manufacturers themselves. That hasn't been extremely widespread. It's used significantly at the tier 1 supplier level, and it's used at the OEM level as well. So I don't, it's not, you don't have to be driving in a complex city scene to be able to take advantage of using simulation to help you with your development efforts.
Great, thanks, Jeff.
Jeff, we got a couple questions online. One is ByWire simulation the same as real-time simulation?
No. When I talk about a ByWire vehicle, I'm talking about a physical vehicle that has been converted, if you will, to give you the ability to connect a computer and access the CAN bus, and in some cases, analog signals, so that the computer can command a steering input or can manipulate the throttle and brakes. The first thing you need to do if you want to develop a new team and begin working on autonomous vehicles is you're going to need a vehicle that you can control from a computer. ByWire is the mechanism of changing that vehicle, or in the case of the company that I work for, Dataspeed, we have kits for a number of vehicles that will grant you access to the CAN bus and allow you to directly command, like I said, throttle, brake, steer, and shift, to do things without a human being actually turning the steering wheel or pressing the brake pedal. That's what a ByWire vehicle is. Now, ByWire vehicle obviously runs in real time. Simulation can run either in real time, under a hard real-time operating system, or there are also cases where you can run simulation non-real time. It depends on your particular use case.
As kind of a follow-up, a similar question, can ByWire simulation be applied on just some components of the vehicle?
It can, yeah. You can. There are folks that have built, ByWire vehicles where all they're manipulating is the steering. A human being is, controlling throttle and brake. But typically, it's throttle, brake, steer, and in many cases even shifting of the vehicle, transmission.
Another question is there a target for a degree of confidence in autonomous vehicles, and how close to that target has the confidence reached?
I am not aware of any specific metrics addressing that. That comes up in many, many conferences that I've attended. It is certainly something that gets discussed in the Pegasus working group. It gets discussed in several of the SAE working groups, but I don't know that I can't point you to a specification or a document that says, here's what it is. That is still being figured out.
Yeah. Another question is, are there any good simulation models of LiDAR, LIDAR, available for research purposes? If you could elaborate a little bit on that, it would be appreciated.
Okay. So when they say research purposes, would this be, that always implies that it's university and, is there an open source tool or something like that? If that's not the case, whoever sent the question in, please clarify it. Let's assume that's the case. I would suggest first looking at a product called Carla, which is an open source 3D simulation engine. It's pretty good. It's certainly the equivalent of some commercial products that are out there. I suspect that the LiDAR model that's in Carla, it will likely be based on ray tracing, which is how most of these models are built, and it will be a pretty generic model. I doubt that there will be very good correspondence with actual LiDAR. One of the problems with building any sensor models is, in this case, if we talk about LiDAR, whose LiDAR are we talking about? Are we talking about a spinning LiDAR, which sits on top of the vehicle? Say something comes from someone like Velodyne, so it spins and has 360-degree coverage? Or would it be a MEMS-based unit or a solid-state unit with a fixed field of view that's typically mounted on the front bumper? Some of the companies that come to name there would be like an Innoviz or I believe Valio, IBO builds a forward-looking solid-state LiDAR as well. So it's, to just say generically, well, I'm gonna build a LiDAR model. There's more complexity in terms of what kind of LiDAR, what nanowave, what wavelength does it run at? Is it 905 or 1550? Is it a solid-state device? Is it a spinning device? How many channels are there? You can head down the rabbit hole very quickly when it comes to building sensor models.
Sure. Another question is, for X number of test cases that are deemed necessary, how much of a challenge is it to define each test case?
Oh, that is the subject of certainly the Pegasus working group. They are working to determine, trying to establish a library of test cases. I don't think anyone has a good feel for exactly how many we're going to need. I tend to favor looking at the behavioral competencies, and then every individual out there, you can certainly look at the list. They're easily accessed on the web, and then you have to kind of make a guesstimate as how many variables do we need to deal with in a given scene to address that competency, and how many different values for each of those individual variables do we want to deal with. It's almost unlimited. You have to kind of look at each one individual, but I can't tell you that in terms of simulation testing, it is in the many hundreds of millions of simulations that will need to be run to even begin to get a feel for whether the software is behaving the way we think it should.
Okay. Let's see if another question. Is there such a thing as distraction factor, as in how many separate simultaneous intrusions can an autonomous vehicle deal with? He said it's probably a little incomplete question, but I guess that's you want to get the gist of it. Do you got enough there?
Yeah, I think I understand the question. Yeah, although that I think, frankly, that's relatively easy to deal with. That's just a question of throwing more computational power at the question. In terms of distraction, there is no real distraction when a computer is doing the calculating, because the computers. That's the beauty if we imagine the future of a fully functional level 4 autonomous vehicle, is it never gets distracted. I kind of look at distraction there as do I have to share computing resources, which means that I can only do these 5 things and I have to ignore these other 2 things, and that's an easy problem to fix, because computers, they follow Moore's law. We can simply add more computational capability to the vehicle so that we don't have to ignore certain things in lieu of others. I mean, that's simple to fix. It's hard to fix in humans. It's easy to fix in computers.
Jeff,
Sure.
this is Jim. Perhaps a simple question, but could you cover the range of sensors and data inputs to a simulation platform? And with the parallel connected vehicle initiative that's out there, do those data objects also matter to an AAV simulation platform?
They do. So I'm going to use a tool that I'm very familiar with. It's a product called Prescan. Prescan is now owned by Siemens Corporation. I don't mean this as an endorsement of their product, but I used it for nearly a decade, so I know it well. In Prescan, there are sensor models for radar, LiDAR, cameras, V2V devices, ultrasonics, and within each one of those sensor categories, there are multiple different types of sensors available. So within the radar model, you can have a very simple radar model that is perfect and always gives you the distance to objects in front of you. You can have a probabilistic model. You can have a physics-based model. There are trade-offs in using the types. As you get closer and closer to a real recreation of the physical device, the simulation gets far more complex to build and run, and computationally it's far less efficient, but it's possible to do. And that is true not just of the Siemens product, but all of the commercial simulation tools will typically offer a library of different sensor models, pre-built models. I think most of the companies will have some kind of a service where you can have a custom model built. And then they also have libraries of, pedestrians and people, are cyclists and other cars and trucks and everything that you would see in a scene. My point is, just because they supply all of that, I'm saying you would be well advised to check the results against actual physical tests that you've run to ensure that, in fact, the assumptions built into all of their models and the material properties and all of that are giving you reasonable results when you compare it against your real world results. That's the piece that even though you're using simulation, you have to go that extra step to make sure that the results make sense.
Thanks, Jeff.
Yes, thank you, Jeff and Jim. I do not see any other questions coming along online. Oh, actually, I did see just one more. This person wrote, real-time barrier is a reaction time. How does your model overcome it? Does that make sense?
I would need more information on what they're referring to.
Yes. Yeah, so if you just wrote that comment, if you want to kind of expand, that would be great. In the interim, I will point out that we will have another webinar in 2 weeks. As Jim mentioned, this is part of a series of webinars. And in actually 2 weeks, we're going to have one on February 4th. The presenter is Mohammed Rashid. And he's going to be talking about North American railways and discuss the development of possible opportunities for North American railways, talk about the possibilities for digital transformation in one of the most environmentally friendly modes of transportation, and how technology is changing the way we see the railways. So that will be on February 4th, starting at 11 a.m. Eastern Time. And we do have a link on our webpage to register for that. I do not see clarification on the question right now, Jim or Jeff, so I think we can probably move on. Jim, do you want to have any other final comments?
Yeah, well, I hope everybody enjoyed today's webinar. Jeff, this was just incredibly insightful. Thank you very much for presenting. As Dan said, we will have a railroad-focused webinar in 2 weeks on including positive train control. 2 weeks beyond that, we're going to have a deep dive into microgrid technology. So feel free to join us for both of those. And if you are interested in participating in the P2784 Smart City Planning and Technology Guide, as I said, we do have a face-to-face meeting the afternoon of February 6th from 1 to 5 in Orlando, Florida. And hopefully we'll see some of you there. So thanks, everyone.
And Jeff, thank you again for participating today, and I hope everybody has a great day.
Yes, thanks everyone. Drive safe.